A quick video here, just going over a couple of terms, and then we'll do an example just to determine if an expression is indeed an odd or even number. So, the first thing I want to talk about is closure of the integers over three operations: plus, minus, and times, but not divided by. And what do I mean by closed? Well, closed means that if I do one of these operations here, plus, minus, or times, with two integers, I get another integer. So if a and b are integers, well, I know that a plus b is an integer. If I add two integers, I get an integer. If I subtract two integers, I get an integer. And when I multiply two integers, I get an integer. Division, not so much. You can imagine 1 divided by 2. That isn't in the integers. 1/2 is not an integer. So division isn't part of this closure that we're talking about. So the integers aren't closed under division because you can get outside of the integers by doing one of these operations. But for adding, subtracting, and multiplying, you take two integers, you add them or subtract them, or multiply them, you're going to get, of course, another integer. The second thing I want to talk about is associativity, commutativity, and distributivity. And I just want to give these names. I think we're all familiar with the concept if I write them down. So associativity means that if we have, let's pick a, b, and c. Let's let those be integers. Then if I add a and b first, and then add c, it's the same thing as adding a to b plus c. And it's the same thing instead of if I add, if I multiply instead. Brackets kind of don't matter if it's just a bunch of additions or a bunch of multiplications. I think we know that. And a lot of times you'll just see it written as a plus b plus c without any brackets, or of course a times b times c, a, b, c. So that's associativity. Commutativity basically means that order doesn't matter. Oh, let me do this in black. Commutativity. This means that order doesn't matter. So a plus b is the same thing as b plus a. And again, the same thing holds with multiplication. A times b is the same thing as b times a. And distributivity means we can kind of factor out common terms or multiply through brackets, whatever we want to say. So distributivity is just saying that if we have a times b plus c, we can, of course, multiply a through, and we get a times b plus a times c. That's how multiplication and division play together. So all that basically means that if I have a bunch of integers that are added, subtracted, or multiplied, then I know I'm just going to get another integer, and that's going to be key for what's coming up here. And I can use the idea of associativity, commutativity, and distributivity to kind of help me do some algebra and rearrange some things. All right, let's look at an example. So let's do a really easy example first. So I have this integer n, and I have this expression 4n plus 15. So I'm asked to determine if this is always odd, always even, or whether it's odd or even depends on my choice of n. So remember that, in fact, I'll write this down as a little reminder, that if a number, let's call that number k, if k is even, I should be able to write it as 2 times some integer. So whatever's in that bracket, if that is an integer, I'm good to go. I know that number k would be even. And if k was odd, I could write it as 2 times some integer again, but plus 1. So that's my goal here. If it's always odd or always even, I should be able to rearrange this into one of these two forms. 2 times something or 2 times something plus 1. So I would say pause the video now and try it yourself. Try to rearrange 4n plus 15 so it either looks like 2 times something, and that something will be an integer, or 2 times something plus 1. And your integer here can be addition and multiplication of some other integers. That's fine. Remember from the last slide, we know that the integers are closed under addition and multiplication. So give it a try. Okay, so now that we're back, the first thing I notice is that, well, this number here, 15, is odd. This number is even. So it looks like I can just kind of remove a 1 from here. Just write this as 4n plus 14 plus 1. And then I could factor out a 2. So let me do that. Let me call this k. So k, I'm going to write it as 4n plus 14 plus 1. And the reason I'm doing that is because I want this in one of these two forms, where I have a bunch of stuff that I can factor a 2 out of, so it looks like this, plus my 1. That's my goal here. I want to make it in one of these two forms. And it looks like both of these terms I can factor out a 2. So let me go ahead and do that. So we factor out a 2, we get 2 times 2n plus 7. And to make sure you factor correctly, it's always a good idea to check if you multiply the 2 back, you get the same thing. 2 times 2n is 4n. 2 times 7 is 14. And we have a little plus 1 here. And look here, we have 2 times n plus 7. Remember, n is an integer. So I have a bunch of integers multiplied and added together. And we know the integers are closed, so this is indeed an integer. So we can say since 2n plus 7 is indeed an integer, we can say that k is odd, since I wrote it as 2 times an integer plus 1. Let's now try this one. We'll do the same thing. Determine if this expression here, 14n squared plus 8n plus 30, where n is still an integer, determine if this is always odd, always even, or it depends on your choice of n. So pause the video, give it a go. Okay, now that we're back, first thing I notice here is that all of these terms do indeed have a factor of 2. So if I factor that out, I'm going to get 2 times some stuff that is added and multiplied together. And I know they're all integers, so that thing in the bracket will be an integer. So let's go ahead and do this. So we know k is 14n squared plus 8n plus 30. And now I'm going to factor out that 2. So I have 2 times 7n squared plus 4n plus 15. Remember, all of these terms had a factor of 2, so I factored it out. And I get kind of a messy-ish expression here, but that's okay. It doesn't matter. All that matters is I have 7 times n plus 4 times n plus 15. It's a bunch of integers added and multiplied together. So I know that the integers are closed, so this is indeed an integer. So I can say, since 7n squared plus 4n plus 15 is indeed an integer, I know that k is even, since we wrote it as 2 times some integer. Remember, that's how we can write every even integer. Okay, let's do one more. What about... let's do this one. Let's do 5n plus 14. Is this always odd, always even, or it depends? So, pause the video now. Try this one. Alright, for this one, you can kind of see, well, this term here doesn't really have a factor of 2 in it, unfortunately. And I can't just remove a 1 because I'm multiplying by n. So it looks like it might be hard to show that it's even, and again, hard to show that it's odd because there's no factor of 2 to pull out. So maybe it does depend on our choice for n. So let's try a few and see what happens. What if... It's always good to do n equals 0 first because that's really easy. Then 5 times 0 plus 14 is 14. And 14 is, of course, an even number because you can write it as 2 times 7. What if, let's try another n. Let's go 1 up, I guess. Let's try n equals 1. Then we get 5 times 1 plus 14, which is, of course, 19. And that's odd. And so here I have a choice of n that makes this expression even when n is 0, a choice when it makes it odd, which is n equals 1. So for this example here, this depends on your choice of n. And this type of idea where we're kind of doing a little bit of algebra and factoring and rearranging things to look like an even or odd number is going to be important to us when we really get into proving statements.